So let's have a look at the first part of this paper by SiddiquiMaribu, which is basically the option to build a power plant which you can then later expand with some additional power capacity. So the idea of this paper, or the topic of this paper, is to consider an investment project by a firm. So we might think of a steel mill or a paper mill, or perhaps even of a greenhouse which uses electricity for the lighting, of course, but also uses heat. So each of these factories might have a demand not only for electricity but also for heat. So what you can do, of course, is to produce those two separately, or basically to buy your electricity from the grid and to have some heating equipment on site to produce hot water or steam or whatever you need for your production process. But an alternative here is to use a combined heat and power plant, or sometimes called cogeneration. So what that means basically is that you have this gas turbine, which is part of your power plant, which you run with the fuel, say gas in our particular case. So this is going to produce, and this generator is going to produce electricity, which you can then use in your factory or for your building, or actually you can also sometimes sell to the power grid if you don't use all of it. But what it also does, it spits out hot exhaust gases. So essentially you can use the heat that's in those gases as well if you need that in your production process. So what you need is some equipment, a heat recovery unit here, in which you cool these hot exhaust gases with water, so that produces, of course, hot water or steam. And then you can actually use your hot water or the steam for the heating purposes for your building, or for your factory, or for your greenhouse. So that's what combined heat and power is. So this involves different investments. So there's an investment in the electricity production over here, but there might also be this additional investment in this heat recovery unit over here, or the heat exchanger as it's called in the paper. So what Siddiqui and Maribu are considering is, well, let's suppose we want to build this local CHP plant on our factory's premises. But what we can do is we can actually phase our investments. So we can, if we are not quite sure whether gas prices will be low enough, we might want to start first with a base load capacity electricity generator, which is more efficient in terms of producing electricity. And then if gas prices might fall further, we might actually extend this. We might extend power production capacity so that we can also cover our peak load demand for electricity once gas costs, fuel costs get lower. But what we can also do is we can add to this initial power plant, we can add this heat exchange equipment in order to basically to produce the hot water or the hot steam. And that's going to be particularly useful if gas costs rise, because we have to produce this heat or steam anyway, so we would be buying additional gas to produce this hot water. But if we can actually use this the heat that's produced by our power plant, well, that's going to be more efficient. So as gas prices get higher, we might instead invest in this heat exchange equipment to take the heat from our electricity production plant. And then finally, the paper actually also looks, of course, at the inclusion of both options. So both the option to extend the electricity capacity and the option to also invest in this heat exchanger to extract the heat. So schematically, this project that the SiddiquiMaribu are considering is this. So you start with nothing, essentially a green field if you wish, or just your plot of land or your factory without any production for electricity. Then we can make our first investment, which involves some investment costs called IEB for electricity baseload here. And if you do this, then you will buy or build, essentially, you get to state 1, which has just your base distributed generation, so your base electricity production unit. And you will do that as soon as the cost of gas, which is here, the threshold for that is called C for electricity baseload, CEB. When the cost of gas falls below that threshold price, then we will make this first investment. So that's like the investment that we considered also in the previous week. So then we have our baseload production plant, and now we can actually go to phase 2. And in phase 2 we can either actually expand capacity, which is what we'll have a look at first. So we can expand our capacity to get actually a peak load power plant, distributed generation, that's what DG stands for. So a peak load electricity plant and on the premises of the factory that costs some additional investment, IEP, and we'll do so whenever the cost for gas, for fuel, is actually going even lower. So when we meet this new threshold, slightly lower threshold C, electricity peak production, then we'll extend this power plant into a slightly larger plant that can also meet peak demand. What we can also do is, and that's particularly going to be relevant if the cost of gas afterwards is going to increase again, we might upgrade this plant with this heat exchanger. So that allows us to also produce this heat so that we don't have to buy additional gas to produce our heat in some separate arrangement, but we can actually take the heat from our electricity plant as before. And ultimately we can go to the final state, state 4, which has both. So it has both this extended peak load electricity capacity, but it also has this heat exchange facility. And so whichever path you take will probably depend on the evolution over time of these costs of gas, C. So indeed, in terms of the setup, what we do have is we have these the stochastic parameter here, so the uncertain parameter. Well, that's the cost of gas, so we call that C. So C is going to follow our favorite process, geometric Brownian motion, and in the paper actually the drift of this cost process is chosen to be alpha, is named alpha, and the volatility, of course, of this process is sigma, as before. So this is the geometric Brownian process that describes the evolution of the cost of the fuel, the cost of gas. So all the other parameters here are just constants. So particularly, so what's the cash flows that's going to be generated? Well, once we have this baseload electricity production unit, it's going to cost us this IEB, so investment cost for the electricity baseload. And what do we get if we make that investment? Well, we get the value of the power that we're producing, which will depend on the price of power, which in this paper is taken to be constant, just long run price that we would pay elsewhere in a long run contract, P, times the quantity of electricity that we can produce through our baseload facility, so it's QEB, so it's also a given, minus the cost of gas that we need to produce this electricity. Well, the cost of gas per unit essentially is C, so we have to scale this by the amount of units, the quantity of electricity that we are producing, and we have to take into account this efficiency. Here actually it's the inverse efficiency, which is actually called the heat rate of this plant. So if that's 2, for instance, it means we need to use 2 units of gas to produce 1 unit of electricity. And then there was an additional benefit, and this additional benefits, well, actually in the paper it's again subdivided into different parts, but here I just summarize this in one parameter, which is called F for electricity baseload, the fixed cost that we avoid by not having to go to the grid to buy our electricity, but having this on site. So we're avoiding some of the grid, of the network costs. So that's going to be an income basically of building this our own production plant. So when we then later on expand this baseload unit with this expanded capacity to also meet peak load electricity demand, again we have to incur these the investment costs, which are IEP, P for peak load obviously. So what do we get? Well, we get the additional production of our peak load electricity demand, QEP, and we have to produce that, again, which is going to involve the costs, the stochastic cost, C of gas, and also, of course, the heat rate, so this inverse efficiency for the peak load plant, which might be a bit higher. And again, there is some additional fixed costs here, which are the avoided tariffs that we have to pay to the network operator to link up to the grid, because we're not taking so much electricity anymore from the electricity grid. And finally, there's this heat exchanger that we might want to invest in at the cost IH. And what we get here is the avoided cost of buying the gas to produce the required heat to the amount of QH ourselves. So this QH already involves apparently the efficiency of producing heat essentially, which is of course very high. So that's the cost of gas that we are avoiding by taking the heat already from our power plant using this heat exchanger, rather than having to buy this separately to produce the heat in some burner essentially. So that's the setup of this model. So what we're going to do is, and what the paper does as well, is first look at a simpler model where we sort of stay away from this heat exchange business. Now we're just going to look at the option to expand the baseload plant into the peak load unit. So in the paper, that's section 4.1. Then we'll look at a second simplification which avoids this peak load thing, but looks at instead at the option to also build this heat exchanger. That's in the paper section 4.2, and in the paper section 4.3 will be the full problem. So I will not spend as much time on that, just because we need to cover the basics, basically 1 and 2 in this lecture. So let's look at what the general strategy is that we will follow here. So what's happening in reality is that we start with stage 0, which is there's nothing yet. We don't have any production plant on site. Then we would go to stage 1, which is having this base unit. So we have to invest this baseload investment costs. Then we get this baseload plant, and then we might go at some point in time to stage 2, which also adds to the peak unit. Well, that's what happens in real time, but how we should solve this, the way to solve this, actually, an easy way to solve this, is by starting looking at what will we have in the end, so in stage 2, and then we work backwards. So what we're going to do is, we know what we have here then. From that information we can start considering, so what's the value of this option to expand the base unit, or in order to get at some point also this expanded stage 2 peak unit. So we will be able to value basically the stage 1 production plan, so the base unit, including this option to later on expand electricity capacity to also involve this peak unit. And then once we know the value over here, then we can step backwards once again to this stage 0 where we don't have anything. And then we ask the question, so what's the value of the option to make the investment into the stage 1 base unit, which also includes the option to expand later as well. So that's the solution strategy essentially here that we will follow. So start at the end, work backwards, so that in the end we know what in stage 0 our options are worth. So let's look at the final stage then. So in the final stage, what do we have? Well, we have these cash flows that we get over time, and we're going to assume that this plant lives infinitely, just to make life easier for us. So this is essentially a perpetuity. So what perpetuity? Well, we have some income, and this income was actually not dependent on C, so this income will be a normal perpetuity essentially. What was the income? Well, once we have the full plant, we're producing power, both the base load and the peak load power, which is with the power price P, which was also a constant in this model. And we're also avoiding these network costs, so that's also essentially income that we get from having this final stage plant with both the base load and the peak load capacity. So this total perpetuity value is this cash flow, which is in the numerator over here, divided by R. That's what the perpetuity is. And then there's the cost. Well, the cost actually scales with C. So this is going to, C was itself a growing process, so this growth rate alpha, if you remember, so the drift rate of this price process C. So what this cost thing is, so which includes both the cost of buying the gas for the base load production and the cost of gas for producing the peak load production. This is going to be a growing perpetuity, so that is a minus because it's a cost, but it's growing perpetuity, so we remember that we have to divide this by R minus alpha to get the value of a growing perpetuity, where again this alpha is the growth rate of this cost here, this cost of gas. So this is the value that we have in the end when there's no more options in place. And now the question, of course, is when we are one stage before that, in stage 1, when we only have the baseload plant, at what moment will we then expand capacity to obtain this final value V2, which includes both baseload and peak load plant? So at what threshold level, CEP, will we make the investment to actually also have the peak load capacity? So we'll do this, of course, when cost of gas and fuel get very low, then it gets more and more attractive to actually build this peak load plant. So when the cost of gas are fairly high, we will not do this. So to the right hand side of this threshold, we will just keep the baseload plant. But at some point, the cost for gas will decrease, will cross this threshold that we're after, we want to know, the CEP. And at that moment, we will make the investment and we will get this final stage V2C, which I just explained over here. And it will cost us this investment cost IEP of adding this peak load plant to the baseload plant that we had over here. And of course, what we want to do is, well, write down what's the general form of the value that we have on the right hand side when costs of gas are still fairly high, but we do have the baseload plant already in place. This final form, this form over here is going to include both the income that you already get from the baseload plant and also the value of the option to invest in this peak load plant. And then we want to smooth paste this value to what we get in the end once we make the investment at the threshold, which is in this left-hand regime over here. So that's basically the program that we need to do. So it's going to happen, so it's here on the slide, but I will also actually do this on paper. So let me do that now. So here we are on paper. So remember that we had in stage 2, the final stage, we had cash flows which involved this P times the base load plus peak load, quantity of electricity, plus these fixed costs, so base load fixed cost, network cost, and the peak load electricity network costs, minus, of course, the value of these EB times QEB, the cost of producing power for the baseload unit minus the cost of producing power for the peak load unit. So that was the cash flows that we had in stage 2, and from that we then argue that, well, we know the value then in stage 2 as a function of C, since it was just this difference of these two perpetuity. The regular perpetuity of this first thing, which does not depend on this stochastic parameter. So it's this, of course. These total cash flows that are fixed, essentially. All these things are just fixed parameters. So this is a normal perpetuity minus this growing perpetuity, since this actually depends on this growing parameter C, growing or declining depending on what the sign of alpha is, of course, and which of course takes this form. Times C divided by R minus alpha, because it's this growing perpetuity. So this is the value that we have from this final equipment, including the peak load unit. So what do we have actually in stage 1? Well, in stage 1 we only have so far the baseload plant. So what's the cash flows in stage 1? We only have baseload cash flows, so we get the value from producing the baseload power and this avoided network cost for the baseload plant minus the cost of the gas for running this baseload plant, which is this. That's the cash flows that we get from production in stage 1, when we only have the baseload plant. But what's the total value then? Well, this value will of course again satisfy the Bellman equation with this now as our cash flow, but with also the option terms. So in general we have these option terms involving beta 1 and beta 2. At some threshold here, CEP will make this investment, where we get V2 minus the investment cost, of course. But here we still have V1. So at this threshold, whenever the costs get, so yes, costs, whenever costs get low enough, we'll make the investment to also include this peak load plant. So V1 in general has both, so it has of course this cash flow terms here, but it will also have the potentially the two option terms, the one involving beta 1, the other involving beta 2. But now we have to of course think about boundaries. Well, there will be the boundary conditions involving value matching and smooth pasting at this threshold, which was going to allow us to find what the actual threshold is. But we also have to take care that nothing untoward is going to happen as the C goes to the right, where there's basically no end, or if you wish, the end point here, and the boundary value, the boundary point here is at C going to infinity. So that's the worrying thing here, or the boundary that we have to take into account here. So we don't want value to blow up at that point, because that's not what's going to happen. If the cost of gas is going to be very high, then we will never make this investment. So we want to avoid the option term that's going to blow up, which of course is now going to be the C to the power beta 1. So that's not going to be there. So the coefficient in front of that power term is going to be 0, because otherwise that thing would blow up as we go to increasing and increasing costs of gas. We don't want that. So what we can have is the other term, so the one involving the negative power, the beta 2 power. So what it means is that the V1 as a function of C will have, well, we'll look at this. Well, we'll first have these cash flow terms, so the perpetuity term divided by R minus this growing perpetuity term, only the baseload part, of course, just like we had here, but just now including the base load terms but not including the peak load terms. These are our regular cash load terms, but now we also have this option term, and I just told you this option term will not involve the beta 1, the positive power, because that's blowing up, but it will of course include this the second term, which I will give coefficient. I'm going to call that coefficient B2 times c to the power beta 2. And of course the things that we need to work out is, what's B2, what's this coefficient, and also what's this threshold here, CEP. So how will we do that? Well, of course we will again use value matching and smooth pasting. So value matching is going to tell us that on the left hand side we have V2. So let me just write it, I guess. P times Q EB plus Q EP plus FEB plus FEP divided by R. Minus, I should say, minus this thing over here. Times C, add the threshold. We're going to evaluate this at the threshold that we want to know. To divide this by R minus alpha, so that's this object here evaluated at the threshold CEP that we want to know. So I plug then C equals CEP over here. We are going to make the investment cost to get that actually, so I have to subtract it, minus IEP. And that should equal, so that's value matching here, should equal the value that we have for V1 at that particular point. So that's going to be P times, I'll put a bracket here actually, P times QEB minus, plus this fixed cost divided by R minus then this cost for the base load, quantity for the base load, evaluated at the threshold, CEP, plus, of course, this option term also evaluated at the threshold, CEP. So this is what we used to call actually C star, right? And so just because we will have multiple thresholds here, we'll give these thresholds more telling names, so with these letters EP here. So that's the name of the threshold to the power beta 2, of course. So this is the value matching condition. We'll also have smooth pasting. So smooth pasting, of course, means we have to look at the derivative with respect to C. Well, if we take the derivative with respect to C of V2, well, this first term is just constant, doesn't depend on C. So, but we do have a term over here. That's the only term actually. So that gives us minus QEP derivative, so the C drops out, of course, divided by R minus alpha. The derivative of the I here again vanishes because it's just a constant. So this is the derivative of the left-hand side, has to equal the derivative on the right-hand side for V1. So the derivative of this object here, again, first part is constant, doesn't depend on C. Second part we have this minus epsilon EB QEB divided by R minus alpha, and the derivative of this object here, plus beta 2, the derivative, times B2 times C to the power beta 2 minus 1. So this is smooth pasting condition. The derivative of this thing over here with respect to C should equal the derivative of that thing, which is this function over here with respect to C. So that's the second condition. So now what's going to be left to us is we have to work out and I have to of course evaluate also this at CEP. Okay, so this is the threshold that we want to know, and of course the B2 is the other thing that we don't know, and we also want to figure out what that is. And of course we can follow now again the same strategy of solving these two equations. Well, let's first of all note that some of these terms actually appear both on the left hand side and on the right hand side. In particular these base load terms, so the P times QEB, we also see that over here. The FEB, we also see that over here, and also this part over here, the base load, the base load part over here, we also see that down here. So I'm already going to just cross that out actually against the similar terms over here. So that's going to make life significantly easier over here. And similarly here, so this part actually also takes place over here. But now we have to go from here. So what we want to do is, of course, eliminate some terms. So I'm particularly going to eliminate the term involving B2. How do we do that? Well, by multiplying the first equation by beta 2 again, and multiplying the second equation by this threshold CEP. So let's do that. What we get then is, well, if we multiply all this by beta 2, we get beta 2. And I'm going to, beta 2 times P times QEP plus FEP divided by R minus beta 2 from this thing IEP minus beta 2 CEP we have over here, but we're going to subtract from that the thing over here, which has exactly the same form. So it's going to be minus beta 2 minus 1 times epsilon EP QEP CEP divided by R minus alpha is going to be 0. So you want to do this yourself as well to check whether that actually is made sense, when that actually works. So this is, we can of course solve this. So let's solve this to get CEP. So in particular we get this whole term, if we put this whole term to the right hand side and then divide by beta 2 minus 1, we get epsilon EP QEP times this CEP divided by R minus alpha is going to be equal to, there was this minus over here, so that's cancelled here because I put it on the other side, but it's going to be equal to beta 2. I divided everything by beta 2 minus 1 times, now this bit over here, P Q EP plus F EP divided by R minus I E. Okay. So now if you wish, of course, you can figure out what CEP is. That's of course the same thing multiplied by the inverse of that. So R minus alpha divided by epsilon EP QEP times what we have over here. And you recognize, of course, this fraction beta 2 divided by beta 2 minus 1. We've seen that before as well. And here we have all these additional cash flows that we get if we invest in this peak load plant minus the additional costs that we incur, namely the investment cost. So that's what CEP is. That's the threshold that we needed to figure out. The only other thing that we still need to figure out is what's this B2, or actually for our purpose, we can work it out later, but you can work it out yourself, and I'll give an example when we do the heat load or the heat exchange investment later on, I will actually calculate explicitly. Yeah, you could do so as well, but we're not going to need it so much in determining the baseload threshold, so I'm going to avoid that for now. You can do this at home. So this is the first part of that analysis. So let's go back to the slide to see what that looks like then. So here we are again on the slide. So again, so what was the Bellman equation for V1? Well, it involved this particular cash flow. So that when we only have the baseload unit, we only have these baseload cash flows, including baseload costs, which scale with C, which grow with C. So this perpetuity part, which is a constant, and the part which scales with C, which gives rise to this growing perpetuity. And then these other familiar terms from the Bellman equation. We had to employ now these boundary conditions. So the one was, if C goes to infinity, then the expansion option that we'll have no value, so 0, the value of that option. So this is going to pin down, which of the coefficients is going to be 0, particularly the one involving the C to the power beta 1 term, that's going to be 0. And then the other boundary conditions at the other boundary, namely at the threshold, C equals CEP, the threshold at which we will make the new investment into this power production peak load plant. There we have value matching and smooth pasting. And then we did I did the computation actually on paper. So this is what V1 is, which solves basically this general solution to this Bellman equation. Took this form, so I used that to indeed find, using these boundary conditions, these value matching and smooth pasting conditions, we solved indeed for this threshold price. So now we go to the second stage. So let's do that in a separate video.